Thank you, Professor Shikha, for that wonderful talk detailing the different possibilities of computational tools that we can use to investigate a biological system as complex as the blood-brain barrier. Um, I would like to start with some very basic questions. What are some factors other than molecular size that would determine the permeability of molecules across the blood-brain barrier?
Uh, the charge is a very important factor. The blood-brain barrier is highly selective. So like I showed you in my data, sodium ions and calcium, all positive charge ions do not go through. So even if the size is similar, if the charge is not right, it will not. Because the pore is very specific amino acids that come together to make it. So if there is a positively charged residue, an amino acid sticking right in the tunnel, it will not allow any sodium ion to go through. So charge is very important.
Okay. How do we experimentally determine the permeability of a drug molecule across the blood-brain barrier?
Very good question. So the first thing that is done is in vitro. What experimentalists would do, they will create a monolayer of cells of the endothelial cells in the brain, and they will have a monolayer, and they will grow it on a transwell. So there will be ions or molecules on the top of the monolayer, and they will study how much is the permeability and how much they are able to collect on the bottom, if you will. And that conductivity tells you whether it is going to go through or not. But that is in vitro. In animals and others, there would be a much harder way to dissect the animal after and sacrifice them.
Um, You mentioned that ultrasound stimulus or an injury usually breaks the blood-brain barrier. Are these tight junctions also impacted by any change in the surrounding chemical environment, like say an inflammation or a disease state like a neurodegenerative disease, like Alzheimer's? So,
Absolutely. Anything that will disrupt the tight junctions will affect the permeability. And there are even cholesterol-related studies where if you increase or decrease the cholesterol in the membrane, the assembly of tight junction changes. So food could be a factor. Elasticity of the cell is a factor. So there are many factors. Mechanical breaking is not the only one.
what about aging? Does aging have an impact on tight junctions?
It is said that with age, there are multiple chemical insults, the word that is used, insults to the brain, and the probability of that increases. But there is no real metric to say. There is correlation, of course. There is correlation that with age that happens. And tight junctions are the guards to this, but it is also what is happening inside the brain and accumulation of proteins that is, the plaques that are formed. The reason could be different, but tight junctions can also affect Alzheimer's.
Uh, what are the other proteins, like say, other than claudins, that would make up the tight junction pores? And even when we come to the claudin family of proteins, are there other proteins other than claudin 5 that differ functionally?
Correct. There are other scaffolding proteins, we call them, the proteins that help support claudin. So those proteins are occludins. Those are in the membrane. There are also proteins that are at the bottom, right under the tails of the cytoplasmic ends of the claudin that really tether them. Those are ZO1s, they call them zonocludins, and many others. Those also are called the whole tight junction complex. However, the reason we have focused on claudin is if you knock out claudin, that's when the permeability changes. If you knock out occludins, it will not change. So functionally, claudins are most important. Structurally, there are other scaffolding proteins. In terms of your question about other claudins, claudin 5 is a member of a 27 claudin family in mammalian cells. And in the brain, there is some expression of claudin 3, but it is claudin 5 primarily. In different tissues in the body, there are multiple other claudins that are expressed, and that's why they have a different permeability behavior.
You mentioned about your research on developing peptides that regulate the pore size. So they are usually administered along with a drug, or like suppose we make drug peptide conjugates. Will the interaction change?
We are testing both. We are testing them by themselves first to just see what is the permeability. If we do a conjugate, the also has to have the deconjugation has to happen inside the brain, and that will require some enzyme or some kind of a unclicking between the two. So that's a possibility that is still under testing.
So all those computational related talks will have this obvious question. Do AI tools will help you take a step ahead in your research?
I would say we are open to every tool that is available. We actually are studying the different hydrophilic and hydrophobic character of the pores that we have and designing something based on what the pore is. And for that, we are doing a lot of simulations and we are using machine learning tools for that. That's a part I didn't get to at all, but that's a different part of our different line of inquiry in our lab.
So we have come to the end of most of the questions from the audience. But I'm sure you have a very inspiring story about your journey as a student from India to now a professor in the Department of Biomedical and Chemical Engineering in US. Can you please share some anecdotes from your journey? That'd be very inspiring for the young crowd attending this talk.
Yes, I would be happy to. Are you able to see my screen?
Yes.
All right.
Yeah.
So I just wanted to summarize with my journey, and it has been a happy journey. Obviously, there are challenges when you move from a country. So I was born in India, in New Delhi, and I did my undergraduate at University of Delhi in the year 2000. I completed that, and then I was at IIT Delhi for my master's, which I completed in 2000. And then I decided that I would go and do a PhD in University of Minnesota as a physical chemist. At that point, I was inspired by the advances in computational modeling, and that's where in Dr. Don Trular's group, I did my PhD. And I was always fascinated by the versatility of computational tools. If you look and see what work I published from 2001 to 2006, it was very physical chemistry. It was photodissociation of ammonia molecule in the upper atmosphere. And I was learning tools and imagining how critical these are to understand what's happening in the upper atmosphere. But when I was looking for postdoc, I wanted to shift gears. And at that time, I moved from the upper atmosphere down to Earth, and I was doing silicates. So how minerals like silicates, which are quartz and most abundant silicates, how do they not dissolve very quickly? Because if silicates were dissolving very quickly, all of us would be swimming and we'd be adapting to be water animals. But silicates keep Earth not from dissolving. So what are the rates computationally? Can we understand the mechanism of silicates? And that was my postdoctoral work. And when I came to University of Minnesota, I was a trailing spouse. My better half, my husband, is a faculty in chemistry, and he got a position in 2009, and I didn't get a tenure track line, which I am in now, until 2012. And for that amount of time, I was fiddling with, what do I really like to do? And I was interested in biomolecules. So for the next 3 years, I was just trying to come up with a research topic that interests me. And when finally I joined biomedical and chemical engineering, which is very different from what I was doing, I'm a chemist by training, but my research was more biological and more geared towards solving biological problems. I was more in the biomedical side, and that's how I ended up in biomedical and chemical engineering department, which from 2012 to now has been beautiful 12 years. And the work that I just showed you, I had no training on, I had never thought I would do it. So I want to inspire all students who are listening. Do not think that you are siloed. If you are a biologist or a chemist, or you're experimental or a computation, do not think that your expertise is going to limit you from what you want to do. I would say follow your passion and continue to collaborate with people, talk to people about what you're interested in, whatever your research ideas is, and you would see that you need a village to really solve a tough problem. And I inspire you to keep thinking beyond your fields. You need the depth in your field, of course, but you also need to branch out, and feel free to do that. And do PhD is the highest degree that you can get in any subject, and it really empowers you to solve the unsolved problem, because there is no other degree that teaches you how to start from zero information in a field all the way to become an expert. So in 5 years, you go from 0 to 100. So please do that. And if you have any questions about how to, traverse this journey and what is academia like, feel free to contact me. I'll be available. Thank you.
Thank you, Professor Shiga, for sharing your wonderful journey and that important advice on share, diversifying and collaborating. How important that is in everyone's research journey. Uh, Thanks a lot. Over to you, Krishna.
Thank you so much, Shriranjani, and thank you so much, Professor Nangia, for that wonderful message. It was really something that was quite inspirational, and it really brings out, the true spirit of, working outside silos, building up like a really multidisciplinary, interdisciplinary approach. So thank you so much for sharing that. And with this, we come to the end of today's session. We really hope that our attendees enjoyed this broadcast. I personally did a lot. And then again, we invite you to view the edited recordings of the past events in the ACS Science Talks library. And at the end of the session, you will receive a brief survey from ACS. Kindly share your feedback with us so that we can continue to improve and serve you better. Finally, on behalf of everyone at ACS, thank you so much for joining us today. We hope to see you soon again for more ACS events. Until then, stay safe, stay healthy. Thank you so much. Bye-bye.
Thank you,
Bye.
everyone. Thank you. Take care. Bye-bye.